In this tutorial, we'll apply the 8 inference rules, or at least some of the 8 inference rules, to some actual proofs. In this tutorial, I'll work 2 examples, and then I'll follow up with some more complex proofs in another tutorial. So let's start with the argument before us. P and Q implies R. P and S, Q, therefore R. So the proof is already set up for us. These 3 lines are the premises, so the proof actually starts from here. So let's talk about a general strategy for looking for a formal proof of validity. This, of course, assumes that we have shown that this argument is not invalid using a truth table. This argument, in fact, is not invalid, so we should be able to find a formal proof of validity. So here's a good starting point: is have a look at the conclusion and ask yourself, where might the conclusion come from? So if you look for R, you will see that the most likely place to get R is going to be from line 1. And what's in line 1? P and Q implies R. So if we think of line 1, and what we want to conclude from line 1 is R, the question is there a rule that would allow us to conclude R from inside of a material implication? And the answer is a likely candidate might be modus ponens. So let's make a little note of that. So what would modus ponens have to look like? Well, the modus ponens schema is a square implies the contents of a triangle. Here, obviously, we have the contents of the triangle, so that's exactly what we're looking for, right? So what the question is, what do we need to complete the modus ponens? And the answer is everything in the square. So P and Q is what we would need. So what we're going to do is look now in the same vein and see, okay, well, what do we need to do? What do we need to do to find P and Q? Well, we have the Q on line 3, so let's look at this. We have Q on line 3. The Q on line 3 could be put together with P if we had P by itself using conjunction. So if we had P and Q on lines by themselves, we would be able to use conjunction. So Q we have on line 3, we would need P. Where can we get P? The most likely place to get P is line 2, P and S. And how can we do that? Well, if you think about your 8 inference rules, and you think about the major operators, there's not very many that have a premise with an and in it. So we can think about simplification. So simplification works like this. We have a well-formed formula in a square and a well-formed formula in a triangle, and they're joined together by a conjunction. Then we're entitled to conclude the contents of the square, which in this case is exactly what we want, P. Now, we have just found P, which we need to combine with Q using conjunction so that we can get the second premise of modus ponens, so we can derive the conclusion of that first premise of modus ponens, and that's what we're after. So because we now have completed the logic of this proof only backward, instead of going forward, we're going backward, right? So what we need to do then is basically work backward. So over in the proof, we'll start on line 4 by deriving P. That's what we got here. And what was the justification for P? Simplification on line 2. All right, excellent. Now on line 5, we're going to conclude P and Q. And that's this step. And how did we do that? By using conjunction. So conjunction on what? On lines 4 and 3. And that gives us the premise That gives us the second premise of the modus ponens, with line 1 being the first premise. So we will conclude on line 6 R, and our reasoning is modus ponens on lines 1 and 5. And since we now have derived what we were after, this proof concludes. All right, so again, a rule of thumb is to make some notes for yourself. That's what I was doing here. But my notes essentially work the proof backwards. So we start with the conclusion and we ask, where can we get it? We could get it from line 1, but only if we had this. Where can we get that? Well, we have part of it on line 3, but what do we need? We need P. Where can we get that? We can get that from line 2 by simplification, and that's the logic of the proof, only in reverse. So the question is, where can we get that? Where can we get that? Where can we get that? And what you want to have in mind for each question, where can we get that, is, of course, the 8 inference rules. All right, now let's have a look at another proof. This is a slightly more involved proof. So look what we have. We have, it's not the case that P and Q implies R. Line 2, R implies not T. Line 3, S implies T. And on line 4, we have S or P. And the conclusion we're after is kind of a strange looking not T or T. So that's what we're after, not T or T. So now here's a question. Where could we get not T or T? Well, if we could get either not T or T on a line by itself, then we could use addition. So we either need to get not T by itself or T by itself, and use addition here to add the other part that's missing. So the addition is this step from here to here. So the question is, can we find a place to get not T, or can we find a place to get T? Well, they're both listed here. On line 2, we have not T. What do we need for that? Well, line 2, major operator is material implication, and so what should come to mind are the inference rules that involve material implication. And there's 3. There's that have this form anyway. So we've got what? We've got modus ponens, we've got modus tollens, and we've got hypothetical syllogism. If we were going to derive not T, and we need the conclusion of this, so it's most likely going to be line 2 as the first premise of modus ponens. Because remember, we're concluding the triangle. We can ignore the fact that there's a negation sign there because it's just a well-formed formula that belongs inside the triangle of the first premise of modus ponens, right? So what would we need for that? To get not T from line 2, we're going to need to find R. And is there an easy place to get R? Well, it's kind of buried in this, and we have no Q. Or we could do another modus ponens. See, that would look like this. Q implies R. If we had Q, we could conclude R, and then we could use this R by line 2 and modus ponens to get not T. But that doesn't look very likely because there's no other source for R out there, right? So let's see if we do any better by looking for T. So the most likely place to get to T is from line 3. And what do we need to get T out of that expression? See, once again, when you look at line 3, that's S implies T. You want to think of the inference rules that have a major operator of material implication. So that's, the usual suspects, modus ponens, modus tollens, hypothetical syllogism. If we were going to make modus ponens work, because after all, we are looking for the consequent of this material implication, what would we need? We'd need S. So that's the thing we need if we're going to do this branch, involving T, and then addition to get T or not T. So what do we need here? We need S. If we could find S someplace, we could get S from line 4, but line 4 has that or in it. That's S or P. So if you see an expression that's got or in it, you think to yourself, oh, that's a premise. What could it be? How about a disjunctive syllogism? What would we need to derive to derive S from a disjunctive syllogism on line 4? We'd need not P. And it just so happens that not P is in line 1, joined to another expression by a conjunction. And so that would be simple enough. We could take the not P and Q implies R, and we could treat the far end over here as the triangle and the P as the square part, and using simplification we can conclude just what's in the square, so that would be not P. So it looks like this is pretty promising. We'll get not P from line 1. We'll use it with line 4 to do disjunctive syllogism to get S. We'll use S with line 3 to conclude T, and that will be the basis of our application of addition to get the other part that we need for the conclusion. So remember, if we have T, then we can use addition to get not T or T. So this is basically the logic of the proof, but backward, since we started with the conclusion. So now we have, because of the notes that we've made, we know this branch won't do the trick, but this will, the branch that concludes T. So let's construct the proof based on this. So what's our first move? So again, above this sort of dotted line is the premises. So on line 5, we're going to derive not P, and we're going to get that by simplification on line 1. Good. On line 6, we're going to do disjunctive syllogism with line 4 and derive S. So that's disjunctive syllogism. And what is our, what's the rule here? It's 4 and 5, because we have two premises, one like this, one like that. And then on line 7, we're going to derive T. And how did we do that? That's modus ponens applied to line 3 and 6. So notice line 3 has the schema of modus ponens first premise. Line 6 has the schema of modus ponens second premise. Everything in the square is repeated. It's just S. And the conclusion is T. Now that we have T, we can use one of the variations of addition to conclude T, to conclude not T or T. So this is addition on line 7. So the way addition works is, let's just review the addition, is if you have something, whatever that is, then you can conclude either that something this way or this way, as long as you use disjunction and put them together. So there are basically two flavors or two variations on addition, depending on what order you need for these. Okay? All right. So we've succeeded because we took T in line 7 and we used addition to add not T or T to the front end. In other words, it's this version. And now that we've got the conclusion, the proof is complete. So we write QED.